Hi, welcome all of you. So, hope am I audible to all of you, right? So, this is the ninth session on the one and two dimensional NMR spectroscopy for the chemist, right? So, I am Vijay Rane. I'm a Prime Minister Research Fellow in Indian Institute of Technology, Delhi. And today we are going to solve some problems based on the topic which are covered in the week ninth of this course. Right. The first problem, before going to the problem, does anyone have any doubts regarding the topics which are covered in the week nine? So if you have doubt, you can ask me right now, or you can ask later as well. But it's good to if you discuss that problem first. All right. If you don't have any problem, then we will directly move to the questions. So here is the first question. The first question is about the question states in the molecule C2H4. The two groups of CH2 protons and both carbons are chemically equivalent, right? Because if you draw the structure of this one, so this is the structure, and if you look at the structure, it has the plane of symmetry, right? So these both CH2 are chemically equivalent, as well as these protons are also chemically equivalent. However, J31H has been determined. This can be accomplished by, so there are multiple options are given. So here, the first option is taking 1S spectrum at higher magnetic field. Second option is taking 1S spectrum at different temperature. Third one given the inclusion of natural abundant 13C as a coupled spin in 1S spectrum. And third option is there is no NMR spectrum to determine the coupling among the equivalent spin. So obviously this is the fourth option is the wrong option here, because as we have seen the course also in this topic, we can able to determine the J3 coupling, right, between hydrogen hydrogen in the uh, ethylene molecule. So to get this J13 coupling, we have to do the inclusion of natural abundant 13C as a couple spin in the 1S spectrum. So then we can get this J13 coupling in this uh, by using the NMR spectrum. So the option C here in this one is the correct option. That is by inclusion of the abundant 13C as a coupled spin to get the J13 coupling in this molecule. Similarly, the next question is here in the 13C NMR spectrum of CH2, Cl2 and CHD, Cl2. There is difference in the chemical shift by 0.13 ppm. This can be attributed to. So if you look at the 13C spectra, if you took the 13C spectra, we see there are three lines due to the CDCl, whatever, or the DMSO solvent. So if DMSO is solvent, then there will be more number of lines. But let's take the example in the we are taking the NMR spectra of this first sample and the second sample in the CDCl3. So this was this spectra observed due to the CDCl3, right? So and then if you look at the NMR signal due to the DCM for the sample one. So you get one signal, and if you have the same compound, like one hydrogen is replaced by the deuterium, at that time we will observe there is slightly shift by the uh, for this is for B molecule, this is for the A molecule. There is slight shift, and the delta, this is the delta values in the ppm, and this difference is about 0.19 ppm. So why this difference is there? So this difference arises due to the electronegativity of difference in electronegativity in the hydrogen and the deuterium. So there is the electronegativity difference in the hydrogen and deuterium, and we call these are the isotopes of each other. So this is due to the isotope effect of this isotope effect, because both isotopes have the different electronegativity, and we know if the central carbon has the two different group attached and they are different in the electronegativity. So in this one there is AA, and in this one there is the A and the B. As the electronegativity of this A and B are different, so we'll observe different in the delta shift value for this carbon atom. So this is due to the isotope effect. The next question here is the selectivity of the dilute spin can be enhanced by polarization transfer from abundant spin. Right, the spin of the dilute spin, sorry, the sensitivity of dilute spin can be enhanced by polarization transfer from abundant spin. The signal enhancement is larger for polarization transfer between. So here, if you look at this one, so this is generally which has an national abundant more nuclei. For that one, the polarization transfer, so signal enhancement is larger, you observe, because if you look at the different whatever nuclei given here, so this is one, sorry, 13C. 13C is generally about 1 point some percent, right? Around 1%, you can say. Nitrogen also, which is not that much abundant. But if you look at the 1H and sorry, in this one, if you look at the 1H, so 1H is quite abundant in the nature, and also in the polarization transfer for the for this polarization transfer, the signal enhancement is higher due to for this 1H as well as the nitrogen 15 uh, spin or the nitrogen 15 nuclei. So we can do the signal enhancement, but comparative the signal enhancement for the nitrogen and the uh, 1H nuclei is higher as compared to if you look at the signal enhancement for this F19 and the 13C nuclei. So for this one, the answer A is the correct option for this one. The next one is the attached protons test distinguished. So as you know, the attached proton test, we can distinguish the CH carbon as well as 13C, right? By using the attached sorry, attached proton test. Also, so here also in the CH2 also we can distinguish by using this attached proton test. So in this one, the option, but if you look at here, it is written only, right? So that's why this option is incorrect. So in this one, the CH, CH3, CH2, and the quaternary carbon, yeah. S- So this option 4 is the correct option here in this one, because by using attached carbon, we can distinguish the CH, CH2. If you have the CH3, that also we can distinguish, and also we can distinguish the carbon because there will be no signal. Uh, that also we can distinguish by using this attached proton test. In the same manner, we have one question regarding the role of spin echo sequence in the polarization transfer experiment. So this one is only for the enhancement of this is like some sort of instrumental kind of question. And I think if you look at all the questions from this week, they are all like theoretical based and informative type questions. So you should know uh, the theory behind this one. So for this one, it is only for intensity enhancement, and do not refocus J coupling as well as the chemical shift value. So it is only for the intensity enhancement. So we can do the spin echo sequence in polarization transfer to achieve to enhance the uh, intensity, but it will not affect the any kind of the J coupling values, also the chemical shift values. The next question is in the 1H and 13C couple spin. So if you have the 1H and 13C couple spin system, the enhancement of signal intensity can be achieved by. So as you see earlier, in the earlier question also, somewhere mentioned, so we can enhance the intensity, right? But in this one, if you look at the 1H and 13C coupling spin system, so here it is 1H is the abundant, but the 13C is quite which is not at all that much abundant. And also in the previous question also, if you see this question, yeah. So in this one, so signal enhancement is larger for this 1H and nitrogen 15 atom, right? So in this question also, the signal enhancement for the 1H is quite larger, right? So to achieve the for this system in which the 1H and 13C both the nuclei are involved, so we do the selective saturation of the 1H transition, and then we measure the signal. So the option C is the correct option here for this one. So the selective saturation of 1H transition, so as we are able to see the transition due to the 13C. The next question is the selective population inversion. Is the similar man question. The selective population inversion, we have given the four options. How we can achieve the selective population inversion? So here the first option given, we give the signal enhancement in both homo and hetero nuclear couple spin. Yes, this is the correct. The statement is correct here. The next statement is works only at selected magnetic field. No, we can do for any magnetic field. Give the signal enhancement only in the homonuclear. If you look at this, we can do for heteronuclear as well. As prior question also, we did for 1H as well as 13C, that's that kind of spin system, right? So we can do for, let's say 1H spin system only, or 1H 13C, that sort of heteronuclear spin systems. So option C is also incorrect on, and do not enhance polarization at all. Uh, this is the wrong. We can enhance the polarization by selective population inversion. So if you have the signal here, so we do the selective population inversion for the 1H1, 1H signal, because it is for 1H it is quite larger signal enhancement as compared to the 13C. So if you do the selective population inversion for the 1H, then we can able to achieve for this heteronuclear spin system 1H 13C, that kind of spin system we can able to achieve the enhancement in the signal. The next question here is about the J J3 hydrogen-hydrogen coupling constant, and where it depends on. So the option A is the relative orientation of the couple spin, right? The next option here is the relaxation time of the couple spin. It will not depend on relaxation time. The strength of external magnetic field, wrong, and 90 pulse field applied. No, this is particular J coupling constant. If you look at the J3 coupling constant, which is depend on the relative orientation of the couple spin. So if you look at the any current different signal here, if you have the CH2 and this CH, so in this one, if you look at this group, this kind of group C, it will have the uh, three protons, right? So let's say one proton in the plane, the another proton is the below the plane, and furthermore proton is the above the plane. So in this type of system, if you look at this is 1, 2, 3. So the coupling between these two protons, that can be detected. So because they are oriented close to each other. But if you look at this linear system in which the here the carbon which has the three hydrogens are attached, and also if you look at here, there will be a two-hydrogen. One is the below the plane and one is the above plane. And this carbon which has the again two protons attached here, and let's say if you, any R group is attached. So because of this double bond here in the first molecule, this hydrogen is held just near to the this adjacent, this highlighted proton. So in this type of system, we can able to achieve the J3 hydrogen-hydrogen coupling here because their relative orientation, they are relatively close to each other. But if you look at these two protons in this one, or these two protons, so this bond rotation is very easily possible because it is bonded by the single bond. This bond rotation is also easily possible because the single bond can easily rotate, right? But if you look at this bond, it is bonded with the double bond. So it is this bond rotation is not at all feasible. So these protons attached to the adjacent carbon to the olefin, and this olefinic proton, they can show, we can observe J3 coupling for these protons, right? So this depends on the relative orientation. So orientation, if you look at the orientation in this molecule as well as in this molecule, although they are separated by the 1 and 2 carbon atom, but if you look at the orientation and interaction in space, they are very much closer to each other, these two protons, compared to these two protons. So that's why we can able to observe the J3 coupling, and which is depend on the relative orientation of the coupling spin. The next question is why we use the TMS as a reference in the 1H NMR spectra. So if you just Google the what are the properties of TMS, and they are good for the 1H NMR, the first property will came the volatile. It is very volatile. So if you do the sample, if you put the NMR sample, right, we add the, let's say we are taking NMR in the CDCl3. So if you have the compound A, we add the compound A about for the 1H NMR, let's say we add about 3 to 5 mg compound, right? Then we add the CDCl3. Let's say we are using the, we are taking the NMR in the CDCl3, right? So we add the CDCl3, right? And we fill this NMR tube with the compound plus CDCl3. And also in the CDCl3, there will be the TMS is already added in the NMR solvent, right? Why we generally use this CDCl3 which has the TMS standard? So the first reason is, so if you after completing the sample, so we have to obviously recover the sample. Most of time, this 3 to 5 mg is very difficult to synthesize. Most of, if you look at the total synthesis, we generally convert A to B, right? B to C, C to D, like this way. There are no n number of steps are we have to perform to get the compound, whatever our target molecule is there, right? So after this, the achieving 3 to 4 mg compound is also very difficult. So after taking NMR, we have to recover back this our added compound A, whatever our molecule we have added for the calculation, we have to recover back that. So what we do, we just took the NMR, and after that we just put, if we put the this all the mixture, this NMR solvent as well as the our compound which you are used for the sample, and if you just keep for the 1 hour, the TMS as well as the CDCl3 get evaporate, and we will get the recover back our compound. So that's the first what you can say advantage of using the TMS. The second advantage is, if you look at the structure of the TMS, which has the one carbon atom, and again, sorry, one Si, right, and which attached to the four different CH3, right? That's why its name is tetramethyl silane. So all these four carbon atoms are equivalent. Also, these hydrogens, they all 12 hydrogens, they are equivalent. So they give a very sharp signal in the 1H NMR spectra. If you look at the 1H NMR spectra, we observe there is one very sharp signal at the 0.0, and that's due to the TMS. So that's the another reason, because this we get the signal due to the 12 protons in the, and for the 12 proton we get only one signal. So if you add very dilute quantity, let's say in 100 ml, if you add 100 ml, if you add only 1 microliter TMS, that's also good enough to show the signal in our NMR spectra. So that's why that we use the TMS as a standard. And also, if you look at here, this answer is the correct. This the TMS is inert and volatile. Yeah, this inert word is also important because it doesn't react with the any other functional group in from our compound. So that's why we use the inert and volatile. That's why we use the TMS. Also, all the protons in the TMS are magnetically equivalent. So as a result, we get the only single peak at the zero ppm, and also all protons are highly shielded and appears at the high field. So as we seen in the when you started the 1H NMR spectra, the if you have the signal enough one NMR spectra, we call this regions as a high field, right? And this kind of signal is as a low field. So it appears as very high field. So whatever the signal of our compounds, they appears in between here in this range. Generally, we if you have the alkyl groups, so alkyl shows around 1 to uh, 2 or sometimes 3 ppm value, ppm, right? So if you have the olefins, they show around 5 to 6. If you have aromatic protons, they show around 7 to 9, right? 7 to 8 or 7 to 9. And aldehyde we have, then it will be in between 8 to 9 or 8 to 10. Or acids may more than 10 delta value, right? So if you look at the most of the common organic compound, they don't have the any signal in this region, which has the for in the region of the TMS. So the signals due to the our standard we are using like TMS will not get interfere with the or will not have the overlap with the our signal due to our sample. So that's why the TMS is the best reference to use in the 1H NMR spectra. The next question here is the regarding the 30 spin and the phosphorus 31 spin are coupled with the coupling strength 51 hertz, right? What will be the nomenclature given for this spin system? So if you look at this, the coupling, which is quite high, coupling constant value, right? So minus 57 hertz. So we call it as it will be a AX spin for this one. If you have the any spin system which has the 13C as well as the sorry coupling due to the 13C as well as the phosphorus 31, and this kind of coupling we call it as the AX coupling here. So this is all these are the all problems from the assignment I have solved as it is. So hopefully you got the answers for all the questions. So does anyone have any question or any doubt? All right. So if you don't have a doubt, I will just stop the recording. There it is.